All right, so hello and welcome back. And today, what we are going to see is we have seen a lot of abstract group theory, and I wanted to give you a little bit about applications, especially about SU2 applications in this lecture today. But before we go on to the applications, we need to build up a little more machinery, and this little part in the front is going to be a little formal, but let's do this. So we are going to define something called, tensor operators. So what are they? So a tensor operator is a set of operators that transforms under commutations of the generators of some Lie algebra, like an irreducible representation of the algebra. Okay. So let's try to find an example. So let's try to define things in terms of SU2s, because that is what we are going to be interested in. So a tensor operator transforming under the spin S representation of SU2 consists of a set of operators, and we're going to call the set of operators OSL. Okay. And so L is going to run from 1 to 2s plus 1. Okay. So what is going to happen is the so this is going to transform in the following way. So so J's are, I've relabeled my T's, which I called earlier as J's. So J's are uh, generators of SU2. So J with OSL is going to give you something like this. Okay, so this is going to be the representation, and that this so this is going to transform in an irreducible representation of the algebra. So we will clarify this in an example very shortly. But so now every irreducible representation is finite dimensional and is equivalent to one of these representations that we found earlier with these highest weight stuff, right? So we can choose all the tensor operators of SU2 to have this form. So let's try to figure out an example. Okay, so let's look at the example of ordinary angular orbital angular momentum. So we have a particle which is in a spherically symmetric potential, and suppose this has no spin. So these J's are going to be equal to just the angular momentum, and this is R cross P, right? So if it's R cross P, that essentially means that you can always write something which is A cross B. uh, the ith component is epsilon ijk ajbk. If you do not know this, I suggest you try and figure it out. uh, so this can be written as epsilon abc rb and pc. So let's try to figure out what this is doing. So let's try and figure out what ja with rb is, right? So ja with rb is epsilon. This is simple. So let's do this. So as I said, if you have two vectors a and b, a cross b, so the ith component of this, as I said, is epsilon ijk uh, ajbk. Now you want to do JA with RB. So this is some epsilon ACD RC PD with RB. Okay, so that's what we have. So now, epsilons are zero plus one or minus one. So this just goes out. ACD goes out. So this is RC PD and RB. Now what? Now what we want to do is you want to figure this one out now. So this is what R C with RB is always, obviously equal to, is going to be equal to 0. So you are going to put epsilon ACD outside. You're going to put RC outside, and you're going to have PD with RB. So this is what, remember, so angular, I mean, this is position with momentum. So this is going to be equal to uh, just uh, I, x with p is I. Now there's a sign as well. So this, as I write out here, so this is going to be minus I epsilon ACD RC with delta dB. So this is equal to I. So RAPA is equal to I, right? So this is what you have, the classical, I mean, not classical, the I mean, uncertainty uh, principle, if you wish, written down in this way. So yeah, so that's that. So quantum mechanics. Um, so let's erase this. So what you see is we have something that we have written down. So JA with RB gives you I epsilon ACB RC. Okay. So if you take RC outside, so as you know, this guy, I mean epsilon ACB is just the adjoint, it's just the adjoint representation, right? So we see that RB, so the vector R, so this I mean operator R transforms in the adjoint representation. So this is going to be, so this, as we see, so it of course this is an irreducible representation of the algebra. So we see an explicit way by which this is done. Okay, so this is the, I mean adjoint representation, and this is a, yeah, and also remember that the adjoint representation would mean this. So this is yeah, so the number that you get is equal to 3, right? So the number, so this is a, I mean this is a 3 cross 3 three-dimensional representation. So it's clear that this r's are going to transform like vectors, right? So that's obviously also clear from other things. But under j this transforms like a vector. Okay, so yeah, a little more formal stuff. So what we can do is we can change to a convenient basis where the spins, uh, uh, where the spin s representation actually is going to appear in one itself. So we can uh, do that. So let's see how you do that. So suppose we have a set of operators, this, I mean omega x, where x goes from 1 to s plus 1, and this transforms according to a representation that is equivalent to the spin s, I mean spin s representation. Okay, what we do, so this j with I mean omega x is going to give you some, or some this spin s, I mean spin s representation. Okay, so that's what you are going to get. So let's see how we use this. uh Now by assumption, d is equivalent to a spin s, I mean spin s representation. That is what we said. So we can always find a matrix S that brings you explicitly from this from the D, I mean D to the S. Okay, so we can find a matrix S that brings us from the, I mean representation of the generators in this in D to the explicit spin S, I mean spin S representation. So you can write this out. You can write this out in the following way. So so this is the matrix. This is LX, and so this is just matrices written here, just to clarify things a little bit more. So this is obviously equivalent to this. That's fine. Now, what we do is we define a new set of operators, and this new set of operators will be given. So OS is going to be given as sum, I mean, omega y into this S inverse. Okay. Now, remember this, that this L runs from minus S to plus S as always. This is 2S plus 1 states. So now what do we have? So you can operate JA on OLS. Now JA, so now what do you have? So you write this out in the way that we have been doing so far. So this is so if you were to use the fact that OLS is given by what you have here, so this just translates into J acting on I mean J acting on omega y. And again, once the so you can do this, I mean steps steps in between. Let me sort of skip this, because this is again just going back and forth with the formula that I just showed you uh, just up ahead as well. So at the end of the day, so what you are going to get, so as I said, that this is going to be explicitly in the in this S in this I mean explicit spin I mean spin SS representation basically, right? So for example, this particular thing is particularly simple for J3, where these L indices just label the I mean yeah, J3 value. So J3S is I mean is as you can understand a diagonal matrix in this. So JS of LL prime is just L of delta LL prime, and so you can try to write this down in so this is going to be just simply OS of L primed into this object. And this object right now, as we can see from here, is going to be just L delta LL prime. So this turns out to be just L times OSL. So this is again, this is a simple, if you wish, it's a generalization of what you know. Okay, so I mean, a few more things that I write out here is that it's not necessary to find this matrix S explicitly. What we can do is so, and we can, if we find any linear linear combination of, say, I mean omega x, which has a definite value of J3, we can take that to be a component of OS, and we can build the other ones by raising and lowering operators. For the example that we did for the position operator, we can we can start by finding R naught. And in that case, we could easily find that J3 with R3 gives you 0. So R3 has an J3 eigenvalue of 0. So that is going to be proportional to R naught. So we can choose R naught equal to R3. And then, the rest of the R's we can just find by raising and lowering operators, right? So that is how you can build up the whole, the whole of this particular vectorial operator, if you wish. Okay, so that was a little sort of prelude into what we were going to do, in the sense that we discussed what these sort of operators are. So when I say there is a vector, vectorial operator, you don't fall out of the sky. Okay. Okay, going from the more formal aspects, now let's look at some applications of SU2. Okay. So we first look at the isotropic harmonic oscillator. So this is a physical system with a Hamiltonian that is given by this. So it's uh, so we are in 3 dimensions. So these x and p are 3D position and momentum vectors. We could write them in terms of harmonic oscillators. I mean harmonic creation and annihilation operators, and we are going to label this as big A's. Okay, so your algebra of the A's is given by this. So AI with AJ, I mean AY with AJ dagger is going to be delta I. Very good. As you know, when we are looking at eigenstates of H, so these are going to be labeled by these 3 integers n1, n2, n3, and the energy is going to be n1 plus n2 plus n3 plus 3 halves, where these n1, n2, n3s are given by these A's acting on the ground state. Okay, very good. So now we wish to analyze its spectrum by using group theory, and so the lowest state, so the vacuum, is going to be one which is annihilated by all the 3 AIs. That's very good. At the next level, so we can have either A1 acting on the vacuum, A1 dagger acting on the vacuum, or A2 dagger acting on the vacuum, or A3 dagger on the vacuum. So we find 3 states. We call this 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we are going to define these transition operators P1, 2, which takes you from 1, 0, 0 to 0, 1, 0, and likewise P1, 3 and P2, 3. Okay. The energy, as it should be clear from here, of these states will be the same. So that means that if you act with, so if you take these p's and you commute it with the Hamiltonian, that is going to give you a 0. Okay, acting on any of these states. So the degeneracy of this first excited levels tells us that there are going to be operators that are going to commute with the Hamiltonian, and these are going to generate symmetries of the Hamiltonian. So what are these P's? So the P's are ones that the action of this is going to be that it is going to destroy. So if you are looking at Pij, so this Pij is going to be something that is going to destroy AIs. Destroy AI. AI daggers, and replace it with the AJ daggers. Okay. Now, if you look at the algebra of these Pijs and you work this out, you would see that this actually satisfies the SU2 algebra. And these then, of course, generate rotations in 3 dimensions, and of course, are angular momentum operators. This is something that you can actually figure out reasonably simply. So yes, so L1 is going to be P23, which is going to be x2 minus x2 P3 minus x3 P2, etc., etc. So these are your angular momentum generators. They are going to commute with the Hamiltonian and reflect the fact that it is invariant under spatial rotations. If you look at how these L's act with the A daggers, this is going to again give you epsilon I case. These give you how these creation operators transform under these rotations. So remember that this is very like what we did earlier. So these are going to transform as vectors. So hence these have to be in the 3 of the SU2. Okay. So these transform as the 3 of the SU2. Now, this was only at the first level, and you can do this to any nth, nth level. And this is where group theory becomes extremely useful. And so, at the nth level, this is going to transform as so the nth level is going to transform as the n-fold symmetric product of this. So this is going to be 3 cross 3 cross 3 cross 3, and this symmetric part of it. So this is going to enable us to break up any state in terms of the product. For example, if you look at the second excited state, so then what we will find is that we are going to so if you do this, so it's going to be 3 cross 3. 3 cross 3 is 5 plus 1. So what you do is if you look at the 5, this is actually the I mean uh, quadruple representation, if you will. So this is going to be so AI AJ, AI dagger AJ dagger plus AJ dagger AI dagger. We have subtracted out the trace, and the singlet is going to be just the dot product. Okay. So in this way, you can build up all sorts of higher dimensional things. So you can build it up at at any level n. In this particular spectrum, only integer spins arise, and we can think of states as symmetric tensors with this trace removed by this delta ij tensor. This is going to be called, this is called an invariant tensor, as if you look at SO3 SO3 transformations, this is going to be mapped to itself. Okay, so yeah. So now we take a short break, and we will just be back with another application very soon.